In this video, I'll be talking about gear ratios. This is a conceptual engineering concept kind of thing. It's not something you CAD. You don't need to like create these things I've CAD'd, but I'm going to talk about them nonetheless. Okay, so let's think about gears, right? They come in different sizes. They have their uses, right? They're actually very important, as you'll find out soon. Okay, but let's think about this, right? Let's say you have two different size gears, and every time one teeth clicks over on this gear, right, one teeth's now passed, like imagine there's a line just going across these two gears. Right, every time one teeth passes it on one gear, one teeth passes that line on the other gear, right? And so we can see that this gear on the left, okay, once it's made one rotation, okay, the gear on the right is not made a whole rotation. It's going slower because it's a lot bigger, right? Okay, and this creates a variable speed. So you can change the speed output, right? Let's imagine the gear on the left is being driven by a motor, and the gear on the right is being driven by a wheel. Okay, I can tell you that the gear on the right is moving at 1/3 the speed of the gear on the left because I know something called gear ratios, right? And yeah, that gives me an interesting measurement, right? And another thing I know is that the gear on the right, there's another value here. It's not just about speed. There's this thing called torque, which is rotational force. Okay? And I know the gear on the right has 3 times rotational force of the gear on the left. Okay, so it would be 3 times as hard to try to stop the gear on the right from turning compared to the gear on the left because of this torque output. Okay, and well, how does this all actually work? So, gear ratios. Okay, gear ratios are always written by you taking the number of teeth on the driven gear divided by the number of teeth on the driver gear. So in this case, what's the driver gear and what's the driven gear? The driver gear is always the gear that's being turned by the motor, okay? And as I was spinning this one on the left, let's say this one is being driven by the motor. Okay, sorry, it is the driver gear, just to be super clear about that. Okay, and the gear on the right is the driven gear because it's just the output. It's being turned by the driver gear. Okay, that's how that works. So gear ratio is always number of teeth on the driven gear divided by the number of teeth on the driver gear. This is a 36 tooth gear as labeled here. We can see that very clearly in the browser, right? And this is the note. And this driver gear is 12 teeth. So we know this is a, you could say, you'd never say 36 to 12. You simplify the fraction. So we'd say this is a 3-to-1 gear ratio. Okay, if you ever write this in engineering notebook, I'll just do it randomly here. Not that this is part of this entry, right? You don't just do 3/1. You use a colon, okay, 3:1 gear ratio. All right, and while you could say this fraction actually just simplifies to 3, you always put the 1 if there is a 1 in the denominator, okay? And that's how you write gear ratios. Okay, so we have this gear ratio here. And what does the gear ratio tell us? It directly tells us the torque multiplier. So since this is a 3-to-1 gear ratio, we know this gear, the driven gear, has 3 times the amount of torque. And the inverse of the gear ratio gives us the speed multiplier. So because this is 3-to-1, right, the inverse of that is 1/3. And so we know the speed of this gear is 1/3 the speed of the gear on the left. Okay, and so this allows you to vary the torque and speed of some kind of mechanism. And why do you do this? When the motor is spinning, right, it has a set maximum speed and it has a set torque it can output. Okay, depending on what kind of mechanism you use, maybe you want to have very high speed, like in a flywheel. The flywheel doesn't require a lot of torque, or you need a lot of torque because you're trying to lift something heavy, like in an arm, for instance, right? Then you need a lot of torque. Okay, and if the arm's a bit slow, doesn't matter, because the way you should think about this is there's some set torque that you need to have in order to accomplish the task, right? You need to have enough rotational force to do something. If it's the arm moving, it needs to have enough rotational force that you can actually move the arm while the claw at the end of the arm is gripping onto like the game object, right? And then given that amount of torque that you like is the bare minimum requirement to make the mechanism actually move, then you want to optimize for speed. Okay, you want to find that balanced ratio that gives you enough torque to accomplish the task, but gives you the greatest amount of speed so you can complete that task as fast as possible. Okay, a 3-to-1 gear ratio like this, when would it be used? I don't know, maybe on like an intake. You don't need an intake to be super fast. Maybe you need it to have enough torque to like push a ball of some sort into your robot, right? So in intake, you need a 3-to-1 gear ratio. Okay, and well, it can get a bit more complicated than that. So we're going to look at some examples, right? Let's say the gear on the left is always the driver gear. The gear on the right is always the driven gear. I can tell you this is an 84 tooth gear and this is a 36 tooth gear, right? So in this example, we take driven divided by driver, okay? And so this gives us a 7:3 gear ratio. So that is the torque multiplier, 7/3, and the speed multiplier is 3/7. Okay, so if we actually set this up on the C channel down there with the joints, so I could actually turn them, then you in sync, then you would see this gear spinning at 3/7 the speed of the gear on the left. Right? Okay, moving on to another example. The driven gear is a 36 tooth gear and the driver gear is a 60 tooth gear, and this simplifies to 3/5 gear ratio. So what that means is this gear on the right has 3/5 of torque, but has 5/3 the speed of the gear on the left. Okay, and the final example, which I find interesting, okay, this is where we have a gearbox set up, and we actually have gears staged on top of each other. And in this case, this is the driver gear, and this is the driven gear. Okay, and it gets a bit more complicated because, okay, let's take this one step at a time. Let's look at each stage individually. Okay, here we have a 12-tooth driver gear and a 60-tooth driven gear. So this is a 5-to-1 ratio. Okay, and it's the exact same thing between these two gears. Okay, this being the driven and that being the driver. Okay, so let's think about this carefully. You have an axle here that goes through both of these two gears. Okay, so that means these two gears are actually spinning at the same speed. Okay, and because they're spinning at the same speed, this means this gear is going at 1/5 the speed of that gear. Okay, so ultimately, oops, why did Fusion do that? Ultimately, between these two gears, we have a 25-to-1 gear ratio. Okay, so when you have multiple gears layered like this in some kind of gearbox setup, then you multiply the different individual ratios to get the final ratio, right? And that gives you a 25-to-1 gear ratio. Use each individual stage as a 5-to-1. Okay, something else I'll point out. Okay, just keep in mind when you're calculating ratios that you can take it a bit slow. Okay, when you're first getting used to this, you just do it one stage at a time. Okay, and you think about which gears have to turn at the same speed because they're on the same axle. Gears on the same axle always have to turn at the same speed. Okay, and that affects the gear ratio. All right, and that's all I have to say for gear ratios for now.